with the lecture, the talk by Auroux from Berkeley about towards relative mirror symmetry of hypersurfaces and their components.
Thank you. So let me start first by two small comments. One is the next event of this collaboration is happening in Berkeley in 2 months, and if you would like to register, you are very welcome to participate, but we need information by mid-February. Okay, so the other comment is that this is going to be a very speculative talk, and there's going to be more conjectures than theorems. So if I write a statement by default, assume it's a conjecture, not a theorem. So the goal is to understand what the statement and partial steps towards functional symmetry for essentially arbitrary hypersurfaces. And I mostly mean in toric varieties for this purpose. For in some dream version that's even more conjectural, this would be in anything for which we understand mirror symmetry. So obviously, so there's a version for complete intersections, which I will not state to avoid getting bulky, but that works. And I should point out also my student Catherine Kenitzo's thesis, which will have to do with the case of abelian varieties.
Do you mean smooth hypersurface? Yeah.
Yes. Okay. So start with the geometric setup, which is, I mean, basically an elaboration on things that have been known for quite a while, but the formulation I will use is the one that appears in my joint work with Mohamed Abu Zaid and Ludmil Zarkov from a few years ago. So start with the following thing. Okay, so let me start with the easiest case for all these hypersurfaces inside C star to the n. So let me start with stating a bad version. Let's say I have a Laurent polynomial in n variables, f. So it's a finite sum of monomials with some exponents alpha forming some finite subset of z to the n. And each monomial has some coefficient in front, which you can interpret either when this is going to be a B model, this will be some sort of Novikov parameter, and so an element of some non-Archimedean field. But when doing symplectic geometry, I will just think of T as a numerical parameter sufficiently small. And the assumption for today is so that mirrors, some of the mirrors are smooth, so not all of them, will be that as T equals to 0, I want this to be a maximal tropical degeneration.
So the toric variety is not necessarily compact.
No, that's right. Things are not necessarily compact. Okay. So then we have a candidate mirror out of the construction. And I will say in the sense of Strominger-Yau-Zaslow, which is in fact a toric Calabi-Yau n+1 fold. So I forgot to have a dimension. This is a dimension n-1, hypersurface in C star to the n. So the mirror will be dimension 2 more, which you can describe by its moment polytope. The moment polytope for this thing is, so it's something in Rn+1, and it's everything that lives over the graph of the tropicalization of F, by which I mean max for all alpha of this linear function with alpha dot wherever you are minus rho of alpha. My sign conventions might be different from those of other tropical people. and equipped with superpotential. So this is not the end. So it's a Landau-Ginzburg. The superpotential is just, in this case, for C star to the n, a single toric monomial with a minus sign in front of it. The monomial with exponents 0001 in this picture. So it's the monomial that vanishes to order 1 on all of the irreducible toric divisors. So just to draw a picture, if I have my hypersurface H0, which goes to some limit which looks like a tropical hypersurface, then the moment polytope for y, in fact, when you look at it from above, so in this example, H0 is a curve living in C star squared, you get a tropical curve in the plane, and you should get a polytope in R3, which is exactly, when you look at it from above, its facets look exactly the same as what you had here. Okay? It's everything that lives above some function here. So in this case, y would actually be, so if I take 1 plus x1 plus x2 plus t x1 x2 equals 0, then this will be this thing called the resolved conifold. And the superpotential will be the thing that vanishes to order 1 on all the facets. So in fact, the central fiber of this is the union of the toric strata in Y. Let me give it a name. That's Z, the 0 fiber. While the other fibers just are isomorphic to C star to B. Okay. All right. So, and then what changes if I compactify or partially compactify? This to some hypersurface H inside the toric variety V. Let's assume that this is non-negative, so if it's compact, then it's Fano, or otherwise the suitable analog for things that are quasi-projective. Okay, and so this is still defined by, I will still denote the equation by F, but now F is a section of some line bundle. Okay. So, the thing that changes, okay, so a line bundle I can think of as being defined on a toric variety. So a line bundle is defined by a collection of weights on the rays of a fan. Of V. Okay, so if you want, this is, let's use the letter nu for the normals of for the rays of the fan, for the normals of the polytope of V. So we have a sum of lambda sub nu, d sub nu, where these are the toric divisors. Okay, so with this understood, then the effect of this compactification or partial compactification is to deform the superpotential on the. So space is still Y, but the superpotential now has extra terms. So we have W sub V, because they mostly involve the toric variety V. So W0 is still the same thing. And then there's a sum, there's some coefficients, which I will not care about. And there's monomials with exponents, which are basically the rays of the fan. Oh, yes, I will verset capital mu. And lambda is So let me maybe give an example because the formula is a bit hard to keep track of. So the running example is just going to be even simpler than the one I had there. The pairs of pants. So pairs of pants defined by the equation sum of coordinates plus 1 equals 0 in C star to the n. So this is an n minus 1 dimensional pair of pants. I will denote that by pi n minus 1. And I could compactify that, for example, to a hyperplane in, well, I think you know what this is anyway, n minus 1 inside P. And that would be P. And so, in this case, okay, so we draw the picture for n equals 2 again. So the tropicalization is max of 0 and the coordinates. So it looks something like this. And now if you stare at a moment polytope that looks like it bends along here, you'll see it's congruent to a standard octant. So in fact, y is going to be just c to the n plus 1. The superpotential for the open case, for the pair of pants, will be minus the product of the coordinates. So z is going to be the union of the coordinate axes. And if I compactify to Pn, then I will add to this a bunch of terms that are just the affine coordinates, with a coefficient in front that you can think of as a Novikov variable or a formal parameter or a numerical parameter, and depending on which side of the mirror you'll be on. So the observation that I want to build on is, if you look closely at the fibers of W0 in this setting still, you will see that the regular fibers I mentioned before, they were C star to the n's. And now if you restrict the extra terms of the superpotential to those C star to the n's, you'll actually find a family of mirrors to Pn, to the ambient variety. Okay? So it works in this case, it works in general, almost by construction. If you look at these extra terms in the superpotential, and you restrict them to the levels of this one, you will find a Laurent polynomial on C star to the n, which just looks like the mirror to V. So the restriction to of W to the fiber, to the regular fiber of W0 is exactly the usual Landau-Ginzburg mirror to, sorry, the toric Landau-Ginzburg mirror to V as a Laurent polynomial with a Kähler form, with a Kähler class inflated by some multiple of a class of H. And this is not an accident. Okay, questions at this point? Still okay? Okay, so the goal of the talk is now to elaborate on the following conjecture, slogan, principle, which is that, so the hypersurface, not quite safe space, so that, say in the case of C star to the n, H0 is mirror to this Landau-Ginzburg model Y with W0, and we expect that the ambient space case C star to the n, is mirror to the typical fiber of W0, in this case C star to the n. And then I want to add to that the complement C star to the n minus H0, and I would like to claim that a mirror to that is actually the singular central fiber, which I've called Z. Okay, which is, in practice, this union of toric varieties. So in some sense, it's a toric degeneration of C star to the n. Union of all the toric strata. And when I compactify, then I will just add WV everywhere. So H in V will be mirrored to Y with the sum of the two terms. The toric variety itself, V, will be mirrored to C star to the n with the restriction of WV. And the complement V minus H I would like to propose should be mirrored to Z equipped with the restriction of WV. So that's the picture that I want to explore and discuss various sides of.
The right is that you see the singular variety only in the model, in a sense.
So, as stated right now, yes, in the bottom right corner, Z being very singular, actually, yes, here and here, Z being singular only has a B model, but of course I'm going to propose an A model based on observations you can make on the B model side. So if you want, the end goal actually is that by the end of the talk we might have a candidate for what's the A model of C. It's not as fancy as it sounds. Yeah. Don't get too excited. All right. And maybe as a comment to that, so in case Maxime wants to fall asleep in a few minutes, the last thing I will say of interest to him is the following comment that maybe demystifies the last row of this, which is that the complement of a hypersurface is itself a hypersurface just in the Weber space. Right? See, the complement of H0 or H is itself a hypersurface in, well, either C star to the n plus 1, or in general, we call that V hat, the total space of O of minus H over V. Okay, and how do I do that? Well, it's just defined by some function f hat of, let me add one more variable for the last coordinate of the fiber coordinate. I will just take y times f of x1 of xn plus 1 equals 0. Okay? So if I do that, then it becomes clear that I can apply my general procedure also to this hypersurface and get a bigger mirror for this complement. So in this way, we find that a mirror is, okay, so we reapply the general process to these larger spaces, and so it's basically an exercise in understanding the tropicalization of this and what things, the other graph looks like. This new mirror is just the same thing as the product of y with the complex line. Let's call u the coordinate in here, and then the graded superpotential is u times w0 plus w sub v, where this one is what I would call maybe w0 hat, and this one is v w hat. Okay, I'm suppressing all the pullbacks, just it's pretty clear what we mean. Okay. So now, of course, on the B model, for dB sync, we can use Orlov's Knower periodicity which says that when you have a Landau-Ginzburg model whose total space is a product like this, and the superpotential has this kind of form, then this is equivalent to looking at the zero set of W0, this term here, equipped with the restriction of the other term. So if you believe in the first line and then you apply it to this larger hypersurface, you also see the last line.
Yeah.
But what's kind of more interesting is to think of whether these things might fit together into some diagrams with nice functors and so on.
Small question.
Yes?
Was general suggestion by Patrick Clark many years ago when you get two dual lattices, you get a collection of terms and you get complete potential one toric variety, potential another toric variety. Is it part of this more general picture?
So I don't quite know about this particular story of complements, but certainly, so the overall construction of mirrors is basically an instance of what was first seen by Patrick Clark and other people. So basically, so in fact when I wrote SYZ mirror, I'm not saying that there's a Lagrangian torus vibration on H itself, but rather on some larger space, which is dimension 2 more. And that larger dimensional space, that larger space is basically, the main feature is it's a Landau-Ginzburg model with more spot singularities along a copy of H. So it has the same A and B models as H. So I think Clark's, so there's a version of that story where you do things entirely with toric varieties on both sides of that construction, and that's essentially what Clark had. Maybe the slight upgrade is in our construction. We actually look at a non-toric setup for the side that replaces H, which gives us a slightly, in the end it's the same thing, but I think the SYZ sees a little bit more because by pushing a little bit away from the toric setup, you get to see a slightly larger chart of the mirror. But in the end, it's essentially an upgrade on that. So maybe I should have said after Patrick Clark and of course. Okay. Anyway, the main new thing was making this more precise in the sense of SYZ.
But so we have some vibration on these hypersurfaces that's sort of like an SYZ vibration.
Yes.
Is there any hope that, like in the future, sort of that we'll understand that as some sort of SYZ structure on these things?
That's a very good question. Right now, I would say there's some hope of doing that in a one-dimensional case where you can just treat it as a combinatorial game. Beyond that, I don't know yet. I'm not completely confident because there are some already in the one-dimensional case there are some pretty nasty. You could always treat this in a Chi-Phi language and then you'll get there. I'm still, old-fashioned and attached to actual geometric constructions involving symplectic geometry and so on. And it's not clear to me that there is a precise meaning there. But if you're willing to kind of abstract the symplectic geometry, yes, so there's lots of things about sheaves of categories that you can do there, looking at Scoletta and some analog, So you're in the business of Scoletta where the fibers are contractible, here the fibers are tori. I think Mohammed's talk will have a few things to say about that. But we're not there yet. It's quite possible that, so by the end of this fight, for the complement, I have this Z candidate mirror, which is not higher dimensional. So one thing you could try to do is in cases where a mirror that's not higher dimensional is available, indeed try to treat that directly as some singular limit of SYZ. In cases where the only known mirrors are higher dimensional, I'm not completely sure what one should be trying to.
What do you mean by higher dimension? You mean the space is higher dimensional, but then it's equipped with a...
Equipped with a super potential, that's right. But so in many cases you can dimensionally reduce that to something singular of the same dimension as H, and in some cases I don't quite know how to do that.
So this is singular guys you can replace by smooth variety with some potential.
That's I think that's kind of the slogan there. And I personally prefer the smooth world, but not everybody is of that persuasion. Okay. And certainly for hypersurfaces, actually, I should have mentioned it. That was later in my notes. So there's, okay, I'll get back to it. Do you know an SYZ version of what you're doing?
Well, there's Falcon has like a sort of stratified torus vibration. Well, yes. The short answer is no.
Okay, I think we're at the same stage on that one. Okay. Anyway, let's move on a bit more towards mirror symmetry. Let me go here so that let's just Let's just stay here. So let's talk briefly about A model on the H side versus B model on the Landau-Ginzburg mirror. So let's start with the affine case. So if I have some H0 in C star to the n, then we expect the wrapped Fourier category of H0 to be equivalent to the derived category of singularities of YW0, which in this case just means, say, the quotient of dB co of Z by perfect complexes. Okay? And so in this formulation, the one-dimensional case there's proofs completely in this language in a paper I wrote with Mohamed, Efimov, Katsarkov, and Auroux, and then in the thesis of my former student, Heather Lee. In higher dimensions, there's statements by David Nadler and by Ben Gamage and Vivek Shende, but usually, so with a caveat, which is that you replace the Fourier category by a sheaf theoretic analog, and also the mirrors considered by Gamage and Shende, rather than being Landau-Ginzburg models, are in fact orbifold toric varieties, unions, whatever, configurations of toric stacks that are essentially dimensional reductions of a maximally degenerate case of this construction. So you can see how, it's a case where you can basically replace Y by a dimensional reduction at the expense of becoming stacky and singular. Okay. So we also have functors in this picture. This is where the fun begins. So there's one functor which is a restriction from the complement, the right category of a complement. This is also a Liouville manifold, for example, by viewing it as a hypersurface. We explained that. And this comes with a restriction functor to the right category of H0. I will try to explain a bit how this works. And so the mirror conjectures postulate that, so here we hope this would be the same as coherent sheaves on the Z. Remember that was this union of toric varieties, and this one would be dB sing of YW0, which is the same as coherent sheaves on Z, not perfect complexes. So of course there's a natural functor from here to here, which is just the natural quotient functor. And so the conjecture is that this commutes. So what is this restriction thing? Well, it's what you get when you have a Lagrangian in the complement of H0 and you ask, how does it go towards H0 as one of the possible non-compact ends in here? Okay. So the informal statement is you want to look at what is the boundary of your Lagrangian L in the ambient space along H0. A more careful way of doing it, well, there's probably many ways, and probably, and I had a brief conversation with Paul, but I think he's convinced me that my way of doing it is probably not the right way. So one way to do this is to use Abu-Zaid and Seidel's Viterbo restriction functor from the complement of the hypersurface to a neighborhood, a Liouville subdomain, which is a neighborhood of that end, to a subdomain that looks like a punctured disk times H0. And once you land in the right category of this neighborhood, you essentially want to project onto the H0 factor, which is easier said to done, but basically, essentially you can think of this as an adjoint to the thing that goes from H0 to H0 times C star, which takes just a Lagrangian to the product of that Lagrangian with R plus. So what that does on endomorphisms or really anything is tensor things by Laurent polynomials in one variable. Where this variable has degree 2. Sorry. Yes?
Question, because with Jan we also have kind of similar stuff, but we need not Laurent polynomials, but Laurent series. What is the mere, what is kind of symplectic picture when you have completion?
Yeah, so there's various completions that could come up in various settings.
Yeah.
Here, I think I'd rather not have series because I want to look at. I don't know. I think I'm happy with polynomials for this. But yeah.
But if it's degree 2, then series is.
No.
I mean, yes,
yes.
In this case, this guy has degree 2. So it has degree 2 if you use a trivialization of a determinant bundle that extends over H0, which is kind of the easiest thing to do here. So I should probably have said also this, the right-hand side here, in respect, if I define things this way, the right-hand side is only Z mod 2 greater.
Because in direct sense, it's already Laurent series.
Yes. So yes, maybe that's part of why. Anyway, so then, so what do I want to say? And then you use basically some 2 periodicity to observe what's going on. So maybe a more useful viewpoint on this is, in fact, there's, you can think of Rho as a localization along a natural transformation. From identity to, in this case, with this gradient convention, the shift by 2, which is induced by, so whenever you have a divisor in a symplectic manifold, especially in an easy case like that, that's completely exact and open and so on, you have an element of a symplectic cohomology of a complement, which comes from counting periodic orbits that link that divisor once, basically. Okay, and this is sometimes called the Borman-Sheridan element. So there's an element, with theta, in the symplectic cohomology with my convention of degree 2 of a complement, which counts orbits that link H0 once. So this is sometimes called the Borman-Sheridan class. Okay, so this element of symplectic cohomology induces, basically there's a module structure for this thing called the closed open map, which says a class in symplectic cohomology acts on Lagrangian Floer homology. Okay. So the observation in this case is that the wrapped Floer cohomology of a pair of Lagrangians, we'll write the restrictions, the n restrictions of a pair of Lagrangians in H0 can be computed, in fact, as a direct limit of wrapped Floer cohomologies in degrees, well, you add multiples of 2 in the ambient space under connecting map in this direct system is multiplication by the closed open map applied to theta. This is just a very, very fancy way of saying when you start wrapping more and more and more around H0, any intersection that you saw somewhere comes back with one more turn and keeps coming back, and all these generators look the same, but in degrees that increase by 2 each time. And you just want to identify all of those with each other and take a limit.
exactly the same description for
Yes, that's exactly the next thing, exactly. Thank you. This matches exactly a method of computation in DBSync. You can compare with the calculation that if you want to calculate harms in DBSync between things that are induced from two coherent sheaves, then all you need to do is you take a direct limit of x in dB of z, this plus 2k, between them.
Also, I mean, it's in localization natural transformation.
Okay.
X2 from identity functor to shift by
Okay.
I mean to itself. And
Okay, so it's also localization by natural transformation. Okay. By, yes, I guess along the mirror to the Born and Sheridan class.
well, but it's more classical.
Yes, yes, probably. So I'm coming at this from the symplectic side. And yes. Okay. All right. So an example where you can kind of check the commutation property under the assumption that this works, or you can rely on Nadler or Gamage-Shande to understand why that side works, is if you look at the pair of pants. So the nice feature is that if you take the complement of a pair of pants, remember this was sum of xi plus 1 plus 0, this is actually isomorphic to the pair of pants in dimension 1 more, by thinking of the graph I told you about. Okay. And so now you have this restriction from n-dimensional pants to n-1 dimensional pants, which basically looks at one pant modeled on the lower dimensional pants. So an example of that is if I look in C star squared, then the two-dimensional pairs of pants, sorry. So yes, C star squared minus one-dimensional pairs of pants, which is basically, I take out the coordinate axis in C squared and take out one more line, which I have backwards, so I can redraw that. It's complement of 3 lines in C squared. Okay. And now an example is, this end here is the one-dimensional pair of pants. Okay. And so, for example, you can look at Lagrangians which are part of the real locus. So components of the real locus. There are actually 2 to the n plus 1 minus 1 of them. And for example, if I take, say, this one, then rho will map it to this component of the real locus of the one-dimensional pair of pants, and so on. So you basically look at what boundary they have along this line, with a shift depending on whether you're to the left or to the right.
How did you choose that one-dimensional pair of pants?
It's a choice. Okay, so what I do is, so on this one I have to choose gradings, and if I choose the grading that comes from having everything in degree 0 for C star to the n, but so if you want, first of all, it's completely symmetric between all of them, okay? But I'm choosing to grade things in such a way that this loop here has degree 2 in symplectic cohomology, while the others have degree 0. And then that's the end that I'm set up to deal with.
So once you've chosen your grading, that choice is fixed forever. You can't somehow interpolate among these.
No, I can keep changing. And so, so there's some subtlety about the Liouville structure. But so basically, I could do this with any of them. So in fact, I have several such functors at the expense of, maybe changing my gradings along the way or treating this all as ungraded or something. Okay. And so now I can match this. So here I would look at coherent sheaves on the union of coordinate planes there. And in fact, the components of the real locus, the proposal is that they correspond to the structure sheaves of all unions of components of this thing. Okay, so take any non-empty subset of the n+1 coordinate hyperplanes, and you can match them by hand. There's an explicit labeling with the components here. And So now there's supposed to be a quotient functor to dB thing, which by Knoll periodicity will be the same as dB co of everything in dimension 1 less. And so basically, on this setup, you can use that to try to work your way. So if you believe that this thing is well understood, as it has been from the Sheafy perspective, then you can check that it matches. And if you believe that it's still lacking a computation purely using Lagrangian Floer homology, then this gives you a blueprint to understand how to do it. So I forgot to say there's a one-sided inverse functor in this case, and in many other cases, that comes from basically lifting, you privilege one component and you take the product with the extra factor and restrict. Okay. All right. And similarly, we expect now if you have a partial compactification, something similar where the right category of a complement should correspond to dB thing of Z equipped with the restriction of the potential WV. I do not quite know how to define the restriction. Morally on objects, it's just you look at where your Lagrangian goes along to H. Depending on whether it's compact or non-compact, might be ordinary Fourier or might be a Pratt category. And you have dB thing of Y with, remember this potential is the sum of the two terms. But of course W0 vanishes on that one. So in fact there's an inclusion push forward functor between the two. And so the expectation is again that this should match. Okay, so this gives, by the way, this gives some very strange mirrors to well-known things. Okay, so for example, if I start with a case of a point inside C star and I try to compactify, so for the complement of a point in C star, which is just the one-dimensional pair of points, Z corresponding to that would be just the nodal curve xy equals 0 in the affine plane. Okay? And then if I start compactifying partially by looking at now C minus a point, which is of course secretly C star, then I get a funny mirror to C star, which is just this singular curve xy equals 0 equipped with a superpotential, say x. Okay? Which is probably the world's craziest mirror to C star. And you can add one more. You can go to P1 minus a point, and you get a mirror to the affine line, which is this curve with x plus y. Probably not the most useful way of doing mirror symmetry for C star, but Sasha Efimov tells me that the computations match. This seems to work. Okay, let me instead move to the other side of mirror symmetry.
Is it well understood the theory of matrix factorizations on non-smooth varieties?
It's written up in a huge paper.
Okay.
Yes, so Sasha Efimov knows how to do it, basically. When I tried, I got always with wrong answers, but he tells me that it can be done, and he has done it. So I will say, ask Sasha Efimov if you need enlightenment what this thing means. I mean, I think the key point that he's kind of conveyed to me kindly is that you should be working with coherent sheaves rather than just...
very bad indicate. You don't have Thompson localization and so on, so you need coherent, have a reasonable thing.
Okay. All right. So let me instead move to the last part, the model on H versus a model on YW. So this is running a project together with Mohammed in various stages of very slow progress. So the case for C star to the n is in progress. Then there will be a sequel that's not yet in progress because we're trying to finish the first one. But I'd like to point out also there's a version of this for hypersurfaces in abelian geometries, which is the thesis of Catherine Canizzo, who's present. Okay, so let's start with the case of C star to the n. The construction that is in our non-existent paper with Mohammed is something like this. So we look again at y and this monomial W0, and we recall that the typical fibers of this look like C star to the n. Okay? And in fact, the fibers along the negative real axis look like C star to the n in an even nicer way, because those ones have a real structure. So there's some Lagrangian L0, which is the r plus to the n, in a distinguished manner. This is completely gratuitous, but it's still comforting. Okay, and now the zero fiber has all of the toric varieties. That's easy. And so now what you can do is, if you take a Lagrangian in this fiber, you can parallel transport it around this kind of U-shaped curve to get a Lagrangian in the total space. Okay? So L0 is obtained by parallel transport. L0. So in every fiber that it passes through, it will really look anyway like something that's like an r plus to the n in C star to the n, but it gets bent by the monodromy as you go around. More bendy. Okay. And so our calculation, then, okay, so we define some sort of fiber-wise wrapped Fourier category of this, which basically involves pushing things around in the base as you would in what's sometimes called Fourier-sidal categories, but fiber-wise, you just wrap in the C star to the n. The two actions commute, so here there's no technical difficulty. So in this setup, you can calculate the endomorphisms of L0. And what you find is, well, L0 and its push-off intersecting two fibers, one here and one here. And inside these fibers, what you will get looks like the wrapped Floer cohomology of r plus to the n. So it will be like the wrapped Floer cohomology of L0, L0, direct sum. The other guys are not canonically L0, but they're isomorphic, so I will just write the same thing as well, shifted by -1. And there's a differential between them, which counts holomorphic sections over this region here. Okay, and this thing corresponds to, so the self-wrapped Floer cohomology of r plus 2vn is Laurent polynomials in n variables. And this map is exactly multiplication by f. So this matches exactly the endomorphisms of the structure sheaf of H0. So that's basically what's happening here. And the slogan is really that this fiber here is mirrored to the ambient variety C star to the n again. And now this action of this idea of transporting Lagrangians along these U shapes is mirrored to restriction to the hypersurface. So now if I move on to instead a hypersurface in a toric variety, then there's a similar story, except we put on top of that this superpotential W sub V. Okay, so add WV respective to the fiber to this whole picture. And so instead of fiber-wise wrapped, what we do in the fiber direction is the Fourier-sidal category category of a Landau-Ginzburg mirror, C star to the n with W sub V. Okay? So you can repeat this same picture. So if you do the same construction, so actually for every line bundle, let's call L sub D, which is O of some I, nu maybe, on the toric variety V, I can build, so Mohammed's thesis tells you how to build an admissible Lagrangian in C star to the n with the corresponding superpotential. And now you can build L sub D in Y by parallel transport of L sub D from fiber to fiber. So of course the key thing to know here is that you can set up the Kähler form on Y in such a way that parallel transport preserves admissibility with respect to the fiber-wise potential. So these things actually make sense. And so now you can reproduce these kinds of calculation. Maybe I should have mentioned, by the way, that starting from here to here is the part of the talk. It's not conjectural. It will soon return to being conjectural for the last 5 minutes or so. So let's say just if you calculate what you'll find, I only know so far at the level of so at the level of a chain complex from LD prime or two Lagrangians obtained in this way from two line bundles. So again, there will be intersections in the fiber at the left and the fiber at the right. The left, you see the Lagrangians you started with. At the right, however, the monodromy that you have here acts in a non-trivial way. And so the observation is that the monodromy about the origin is mirror to tensoring by O of H. And so in fact, I think which I called the weights were lambda. So this is L sub lambda, and then prime minus lambda shifted by -1, and now the connecting map will again be multiplication by n. Okay, so this is basically just mirror to the way in which you can compute things on the hypersurface H by resolving from the ambient space. So what you expect, something like this, the restriction functor coming to H, and so let's call cup this functor that just transports things along these paths. Where this thing is this slightly funny version of the Fourier category of this potential, where I've actually split W0 and WV and treating them in slightly different ways. But conjecturally, that's the same as just putting them together. Okay. So now, the last 3-4 minutes, I want to talk about the complement and this singular mirror and what does it mean that we expect the complement of H to match with the singular fiber equipped with WV relative to Z. So the observation here is we could try to define, basically, the Fourier category of Z, like this, by localization. In the following way. So Z is really the singular fiber in this map U0 from Y to C. And they say the monodromy around the origin is a twist, basically, that's kind of mirror to tensoring by O of H. So there's a natural transform, so there's a natural functor. give it a name. Let's call it mu, monodromy, acting on the fiber. Mu acts on the regular fiber in a way that's mirror to tensoring by O of H. And moreover, there's a natural transformation from identity to mu, which counts holomorphic sections of this vibration over a disk centered at the origin. Okay, and this natural transformation corresponds to just multiplying by the defining equation of H. That's basically why these calculations turn out the way they are. And so now the natural thing to do in this context, since after all you get to the complement of H from the ambient space V by localizing along multiplication by F, is exactly that. So natural candidate is to define things by localizing the Fourier category of a generic fiber. Let's say the fiber at -1 is when I like best because it's start at the end. V along this natural transformation. Okay, so for example, for the pair of pants, which is C star minus a point, the mirror Z would be just the union of two affine lines. It's a nodal thing like this. And what you want to imagine is that this is a singular fiber and something where the regular fiber is a cylinder. The monodromy is a Dehn twist. Sorry? What? Okay. Yes, and so the monodromy is a Dehn twist about the equatorial S1, and the thing you want is the quotient by that S1, which is the same as localizing along the Dehn twist. In higher dimensions, you have these kinds of family twists along the tropicalization of H, whatever that means. You can write it explicitly, and you want to do something similar. The other thing you could do instead, in the last 30 seconds, is you could instead use stabilization and stay in the smooth world. Namely, you could define the Fourier category of Z as the Fourier category of this bigger than the Ginsburg model we had, Y times C, equipped with its potential U times W0 plus W sub V. And so the evidence for the fact that these two are the same is that you can build a natural functor from the Fourier category of, let me drop the WV because it's not very important. You can start with this thing, and you can lift it. So this is C star to the n. You can go to C star to the n times another C star, which is going to be the regular fiber in the other one. This is just a product with R plus. And then you have this cup functor at parallel transport. This is the fiber of W hat 0. And then there's a cup functor that goes into this larger space Y hat in there. And so under mirror symmetry, this just corresponds to go from H to H minus V. One thing you could do, which is really dumb, is to go from V to the complement of H. First thing you do is you go from V to the total space of a line bundle over V by pullback. And then you restrict to the graph of 1 over F to get to the complement. And that's just mirror to that. So it should be the same. Okay, the end. Sorry.
Questions?
So, in this sheet theory picture, we have a way of interpolating among all the different possible singular Z's, and maybe also to the matrix factorization mirrors. Do you have sort of some way of understanding that?
So so I think what you mean is when you can change the mirrors by flops by choosing different tropical limits of H. So of course, if you're interested in the A model of the mirror and the B model of what you started with, these are inequivalent because these are different large complex structural limit points. If instead you do the other side, so the A model on H and B model on these mirrors, then you expect these B model categories to be equivalent, essentially because it's a bunch of flops. And certainly the Fourier category on the A side doesn't care which complex limit you took. So I don't have an explicit statement, but it's part of this general, fact, feature, whatever, that flops don't really change the B model.
So this localization naively, could it be understood that in the end you have some singular Lagrangians, maybe immersed with local systems which agree on what you constructed?
So I would love to understand it this way, but I do not know how to make sense of that. Yeah, I mean, it would be really nice to get a more direct explanation of what's the Fourier category of this, and I should say actually on the one-dimensional case, there's the very, very early stages of something I'm trying to do with Ludmil and Sasha Efimov and Andrew Harder, but we don't really have much to report yet. So.
Okay. If there are no more questions, then let's thank Denis again.